The world of nanotechnology is populated with small objects, many of which must be very strong to perform their function in a reliable way. These include the nanoscale computer circuits shown on the left, the very thin hard coatings on the hip and knee joints in the middle, and the nanoscale machine elements shown on the right. Exactly how big is a nanometer? As shown here, a human hair is about 50,000 nanometers across. In comparison, a spider silk is about 1/10 this size. The nanopillars I will discuss later in this talk are about 500 nanometers, and the computer transistor shown on the right is only 50 nanometers, or 1/1000th the size of a human hair. Over the past 30 years, our research team at UT and ORNL has developed techniques to measure the strength of these nano-objects. The primary tool we use is the nanoindenter, a precision instrument that drives a hard diamond indenter into an object while measuring the nanoscale forces and displacements required to do so. The nanoindenter can test objects as small as 10 nanometers. In addition to measuring nano-hardness, the nanoindenter can also do nano-pushing and nano-pulling. Nano-pushing, or compression testing, is often conducted on nanopillars. Nano-pulling, or tension testing, is used to measure the strength of small diameter fibers, such as the enormously strong black widow spider silk shown here. Another important enabling tool in nanotechnology is the focused ion beam mill and microscope, like the one shown on the left. This instrument uses a highly focused beam of gallium ions to mill and sculpt very complex nano-objects like those shown on the right. We have recently designed and built a system performing nanotensile tests in an electron microscope. This allows us to image small objects at magnifications up to 1,000,000 times, pick them up with a nanomanipulator, and fasten them in place for testing with a nano-welding system. We can measure the strength of fibers with diameters as small as 50 nanometers. With a nanoindenter outfitted for nanocompression testing, we have recently measured the strength of the 500 nanometer molybdenum pillars shown on the left. These pillars exhibit enormous strength. In fact, they are about 10 times stronger than high-strength steel. This gives rise to the common mantra in nanoscale testing that smaller is stronger. In addition to material science, nanomechanical testing is now commonly employed in many other fields of science and engineering. As shown here, geologists frequently use nanoindentation to probe and characterize the hardness of rocks, such as the colorful striations observed in this specimen of the mineral zircon. And in another geophysical application, scientists are now using nanoindentation to bridge the mechanical length scale from nanometers to kilometers as they probe the strength of very small particles residing in geological faults that determine their frictional behavior and are ultimately responsible for large geophysical events like earthquakes. In this case, nano controls mega. There are numerous applications in the field of biology. For example, the stiffness of tree cell walls is found to vary in an amazingly consistent way, with one side of the cell being much stiffer than the other. Curiously, the stiffer side is almost always aligned with the non-stiff side of the adjacent cell. Why Mother Nature does this is not yet fully understood. Another example from the bio world is shown here, where MIT scientists have used nanoindentation to understand the unique armor of an unusual snail that lives in the lightless world of a hydrothermal vent 10,000 feet below the sea. Nanotesting has revealed that the armor is exceptionally strong because of a unique combination of hard and soft layers. In the realm of medical science, scientists are now routinely using nanoindentation to unlock the secrets of what makes bone so strong. As shown in the middle frame, one of the important trade secrets employed by Mother Nature is to alternate stiff, brittle layers with soft, plastic-like layers that resist cracking. Did you know that hardening of the arteries is actually caused by the formation of a hard, calcified plaque on the inner lining of the blood vessels? Medical scientists are now using nanoindentation to study these structures and use the new information to develop new treatments for the numerous diseases caused by this condition. In a recent publication, anthropologists have used nanoindentation to reportedly solve the mystery of the Lockyer Sea extinction, a prolonged period following the eruption of a German volcano 13,000 years ago, during which there was no human habitation in the area. In this paper, the scientists explore the hypothesis that the volcanic ash was especially hard and abrasive, and that this caused most of the grazing animals on which the humans depended for food to die away after their teeth were worn away by abrasion of ash-laden vegetation. The hypothesis was tested by showing that the nanoindentation hardness of the ash particles was much greater than the foraging animal's tooth enamel. And if you believe this explanation, I also have a bridge I would like to sell you. In the very unusual application shown here, materials engineers have used nanoindentation to probe the mechanisms of plastic deformation in RDX plastic explosive. Under normal circumstances, this would be very dangerous, but because the tested particles are very small, they do not explode when mechanically deformed. And finally, two specialty applications from East Tennessee. As shown here, NASCAR racing recently got turbocharged when nanoindentation methods were used to characterize the mechanical behavior of the various layers of rubber used in high-performance tires. The new nanomechanical data has been used to optimize the tire design. The other East Tennessee application is one of my favorites. In 2011, Sarah Herbert, an 8th grader at King's Academy in Seymour, noticed a claim on her shampoo bottle that this shampoo strengthens the hair fiber after just one use. Having access to our nano-tensile testing system through her father, she turned this into an award-winning science fair project. Using her own hair for test samples and controls, Sarah measured the tensile strength before and after washing with the shampoo. The results are shown in the stress-strain plots in the right-hand figure, where the black curves are the controls and the red curves show the strength after just one Washington. I'll let you draw your own conclusions, but remind you the title of her poster was Marketing Hype, Fact or Fiction. Well, as Porky would say, that's it, folks. If you'd like to learn more, much of what I've presented today can be found in a review article written by Warren Oliver and me in 2011. Warren is a close friend, a UT grad, and the founder of a very successful Oak Ridge company that manufactures world-class nanoindentation systems. Thanks for your attention.